Thank you. Okay, so this is the third hour of week 5, and we were talking about a data structure called stack. You'll remember we had some slides how to use stack, and before that, what stack is all about theoretically. Then we've done some limited practical examples, and as you may have remembered, as you may have remembered, I've given this as a homework to you. Go home and do some examples on Kale, I said, and hopefully you did. I'm going to go over a simple example because this is a screenshot of Kale, as you will easily recognize. Very simple code, and I'm checking what's happening in each line. And after each debug line, when I press 10, I've taken another screenshot like this. So at the next slide, it is like I've pressed F10. So this will be what's happening when you work on Kale. So when you work on Kale, you put breakpoints and use F10. So I'm not going to go all over this example, but I'm going to point some important things about this practice so that when you go home and do this homework on your own, you will understand it better and you'll know what is important and what to check. So basically, these are some lines of code. And we are loading some values to registers. And if I have this yellow triangle, the yellow one, be careful, here, it means that I'm currently executing and I've stopped my execution at this line. I have not executed this line yet. The yellow triangle means that in Kale. So I am about to execute this line. When I press F10, it's going to be moving to the next line and I will be executing this line. So I have freezed the code here and I've got the register bank here, the register values and the special function registers, the stack pointer, the LR, PC, whatever. So let's try to analyze what these are all about. So I'm going to be trying to use my famous code again. This pen again, not code. Guys, this is the instruction memory. In this part of the memory, I have my instructions. So I have an instruction like this, which is push R0. So I'll put push R0 here. So for example, I've got push R0 here. I have this line of code push R0 at some place in the instruction memory. What is that place? Can anybody tell me? Because I can't see it on the screen. It's written in PC because PC always points to the line which is going to be executed. So looking at PC, I can easily say that. Let me write with another pen. This line of code in the instruction memory is at this location. I'm reading from here, guys. So 0, 0, 0, 0, dot 0 to EA. So guys, this is the exact line of code here. So this is this part of the memory. And the next one will be another place. We're going to see what is the next one. Any question? Okay, so similarly, I told you that before what is similarly, the instructions are in somewhere called the instruction memory. However, the data is kept in a place which is called the data memory. If you remember the architectural schema of the cards, they were separate places, instruction memory and data memory and registers, separate places. However, when I try to draw that, I use a similar notation, guys. So imagine I'm drawing the data memory. Let me draw the data memory somewhere here, okay? I'm going to be using the same notation. So it's like bank of cells, bank of cells. And let me say this is the data memory with my perfect hand written. Okay, so in the data memory, These are not the registers. Registers are somewhere else. Registers are, in this example, kept here. So I'm not drawing a register bank for the registers. They are already here. I can keep track of them. Why I've drawn the data memory? Am I reading something from the memory? Yes, actually, the contents of the stack are written and read from the memory. So guys, imagine I have nothing in the stack. Thus, the stack pointer is pointing to a place in the memory. For example, imagine it's pointing to here. So I would say that the stack pointer is pointing to here, which means if I call a push instruction, it will get a value from the registers and write it starting with this part of the memory. So at this line, I'm pushing the value inside R0 to this data memory. What is the value inside R0? It is 0. So if I execute this line, 0 will be written to this place, and where stack pointer points will change, because that's how stack works. Does it really happen? Just let me write 0 here so that I know that I've written 0. And let me get to the next slide. I'm getting to the next slide, guys. I'm at the next slide. So I have executed this line. Now let me check. What is the, sorry, I forgot something. I forgot to tell you something. In the previous one, the value of the stack pointer was this value. Before I executed this line, because the yellow triangle is showing this line, so I have not executed it yet. The value of the stack pointer was this. So which means actually, the value of this address in the data memory is actually that exact value. So guys, SP is equal to 0 to 400. I have read it from here. So this stack point, so the address of this location is this. Okay, so if I push a value to the stack, I'll be writing that value, and the stack pointer will be pointing to the next location in the stack, right? So in that case, the value of the stack pointer will change, I'm expecting. That's how you check how things happen in Kale. Is it really so? Let me get to the next one. Well, yes, the stack pointer changed. Now the stack pointer is pointing to this place. This place. And now the value of the stack pointer is changed. As you can see, I'm reading the value from here. 3FC. It's another value. So it really changed. How much did it change? Actually, comparing to the previous value, its value changed by some number. Why this much number? Why? I mean, why? It didn't change only one. If it changed only one, it would have been 3FF, because it's decreasing for some reason. It wasn't 3FF, it wasn't 3FE, it wasn't 3FD, 3FC. It changed by 4 bytes. Why? You don't know this yet. This is about the organization of the memory. And the organization of the memory we are going to see next week. When we learn how the memory is organized, how big the cells are, each cell are, you will understand this detail. But for now, just concentrate on when I push the stack, when I push a value into the stack pointer value changed. That's what I'm trying to show you. Okay, and be careful. Now I'm about to execute this line of code. What is the new value of the PC? The new value of the PC also changed, and it increased. Now it's showing another location, and it's increased by 4 again. As you can see, it was EA. Now it's not 4 bytes, 2 bytes. EC. Why? Why? Still, this is about the organization of the memory. Very simply put, this instruction was 16 bits, and it was 2 bytes, and it had to go 2 places. Well, you don't know this yet. You don't have to understand this, but I'm going to be explaining to you why SP or PC changed by 4, decreased by 4, or PC was increased by 2 or 4. We are going to explain this. These depends on the size of the instruction and the size of the cells in the memory. But you can also see that as we go along the code, executed lines of code, PC also changed as promised. That's how you should be debugging a code. For example, in the next line, do this yourself. Push these values. You want to check which value was pushed first. Then push these values, and is R1 pushed first or R3 pushed first? Well, depending on the definition of push, you can know this, but you can also check it. Imagine you do this operation, then you pop a single value. If you pop the single value at R1, then R1 was first. Or if R3, it was R3. So you can do these checks on your own. Any questions about this example? Okay, good. We are going to be covering examples, don't worry, in Kale. And when we learn memory organization, these examples will make more sense to you. But these slides show you how you should be making these debugging tests. Now, okay, you have an idea of how stack is working. Okay, good. In the definition of stack and push and pop, I've omitted these lines. I've shown you how to push registers and how to pop registers, of course, push and pop. And there's also a definition here. And for push, it is only LR. And for pop, it's only PC. While I was talking about push and pop, I'm sorry, push and pop, I told you that you can only push values from the registers. You cannot push values from the memory or somewhere else. Actually, I lied. There is an exception. You can also push the LR value as well. What does it mean to push the LR value? It means that you have these values inside. When you push the value of R0, what happens? You push that value, get the value inside R0, and write it to that specific location, right? And it's the same. R0 is a 32-bit register. LR is also a 32-bit register. And there's a 32-bit value inside it. When you push LR, just like this, no, this is R1, sorry. I'm sorry. When you push LR, what happens is you get the value inside LR and you put it into the memory. And the same is for pop. When you pop PC, you get the value inside stack and write it to PC. So push is from here to the stack. Pop is from the stack to this register. However, be careful, guys. You cannot push PC or you cannot pop LR. You can only push LR other than our registers. And you can only pop PC other than the registers. These are some exceptions for the usage of pop and push. Why do we have those exceptions? Actually, there's a very solid reason for that. And that's about the nested subroutine calls. I mean, it doesn't make sense to you right now, but it's going to make complete sense to you. So we can push LR and pop PC. Why? Guys, actually, we do this to jump to subroutines. So how did we jump to subroutines? Remember the BL instruction? BL instruction was special. It did two things. The first thing it did was, it was just like a branch instruction. The program counter value was changed to this label, factorial. So factorial stands for an address value in the instruction memory. And if we change the program counter to that value, we execute the code which starts at that address, which is the factorial subroutine. Okay, the first thing it does is what all branch instructions does, changing the PC value to the factorial. Good. The second thing was, well, if it didn't jump, it was going to execute the next line of code, right? And the next line of code is written somewhere in the instruction memory. When we are finished with this subroutine, we want to get back to this place. So this is our return to our home, way back to our home. It saves it to the LR so that when we return, we know where to return. But this architecture is very good. But what happens if there is a nested subroutine call? What is a nested subroutine call? Imagine, guys, I'll try to define it for you. A nested subroutine call is, imagine I have a code like this one. So I could move. Imagine this is the main code, and I've got this factorial. And inside factorial, I do things R0, R0, 1. And at that code, I have another jump to a subroutine. BL something, BL power. I have another subroutine. And I just have my code. And at the end, I say BXLR. This is how I return to here, right? And at some part of the instruction memory, I also have power. It is like, can you see the lines as I write them? I don't know how it works. Can you see the text box?
Evet, görünüyor hocam.
Because
Görüyoruz hocam.
Thank you. So there's another subroutine, which is LDR, R1, for example, 0, 3. And it has some lines of code, and it says BXLR. There's a big problem with this code, guys. And I'm going to show, sorry. That's it. There's a big problem with this code. Let me show you what that problem is, guys. The problem is, for example, let's see what happens. For example, I've got the registers, and let me try to write the registers. I have LR. So I have LR here, link register. So when I did BL, for example, this is an instruction memory. This is like the instruction memory, sorry. This is like this. This is like the instruction memory. And these are all lines of code in the instruction memory. And for example, in the instruction memory, this is A something something 0. This is A something something 1. And this is A something something 2. When I do BL, it will jump to factorial so that the program counter will change. And my way back is this instruction, right? And it is at this value. So when I execute this BL inside LR, I will be writing this value, right? 0, A, something, 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 2. Why? Because when this instruction is finished, this BXLR will get the value inside LR and write it to PC, for example. Let this place be PC. It will write it to here so that I'll be returning way back home. Any questions about this? But be careful, guys. There's a problem here. There's another BL here. What? Okay, you started factorial program counter. Let's continue. And this is also an instruction memory line. So in the instruction memory, this is something, for example, let's say B something something 1, 0B something something 2, and 0B something something 3. There's the lines of code here. When you call BL, it will do the exact same thing. It will change the program counter so that it will execute these lines of code, and it will change the value of LR to this next line. So it will be deleting this, and it will be writing 0B3 here. Okay, good. When I come back, when I'm inside LR, I will be returning here. I will continue. But when I call BXLR again, I have lost my way back home. I have lost this value. It will be just turning like this. So actually, it is impossible to call BL inside a subroutine, which was already called by BL. Can you see the problem here? Any questions? Nested usage of branch with link will make you lose your link register for the main code. Can you see this problem? Okay, any questions? And that's the problem. So when you're calling functions from functions, actually it is not possible to use BL. You need another kind of mechanism. And actually that mechanism is push and pop PC. How are we going to do it? I'm going to be showing you very clearly. So when a subroutine calls another subroutine, it cannot just use BL because it will overwrite the link register. Because each time you use BL, you lose value, the previous value at the LR. It is overwritten. There are no multiple LR. There is only one single LR. When you write something to LR, that the value inside link register, the previous value is lost. So you have to save the LR to somewhere. So before you call that function, save that value to somewhere so that you don't lose it. Okay? Good. How to do it? Actually, there is a very nice example for that. And this was 3 years ago, a lab assignment. But today, we have all the solutions of those assignments. Why this was so? Because this was a subroutine which called e to the x. And e to the x mathematically has this Taylor's expansion. You can calculate e to the x by using values of x. I mean, you can use up to some. This goes to infinity, but you don't do it infinitely. You construct a loop for that. We're not going to cover this, but I'm going to be covering a very simple example. But this guy needs a nested call. Why? Because inside a for loop, it's always going to calculate x to the n over n factorial. So it is like it's going to call factorial and power routines in a nested manner. So guys, let's try to see this. How are we going to do this? I'm going to be opening the example, but sorry. Okay, so guys, how can we do this? Actually, when you call something, what you can do is you can use push LR and pop PC inside the first subroutine. So what happens here? For example, there's an e to the x subroutine, e to the x function, and it needs to use the factorial inside. You don't know how it's working, but it is the factorial. I'm going to go over this code very simple, in simple terms, just like I did previously. So I'm going to be drawing the instruction memory. So guys, this is the instruction memory, right? So I'll consider this as an instruction memory. So this line has a value in the instruction memory. So imagine this is at line 0, 0, 0. So this is at line 0A1. So this is at line 0A2. And there's another code here. And that should be at line 3. So guys, when you do BL, what happened was, there was the LR. When you executed this guy, the LR value was set to the next execution code, which is 3. So that when I come back, it was going to be overwritten. Okay? So I use BL inside as well. So if I use BL, this value will be lost. But what I do is, before I do anything in this function, I push the value inside LR to the stack. So I draw the data memory here as well. Let's say this is the data memory. And there is nothing in the stack, in the data memory. It's empty now. I push LR. I get the value inside LR and write it to the first location inside my. Okay. Now I have my stack deleted. So stack is pointing to the next place. Okay. And I do some operations. And I call factorial with BL. Okay, this line of code as again. These are some lines of code. They exist somewhere in the instruction memory. So for example, this is at the instruction memory B something something 1. This is at the instruction memory B something something A, for example. The next line of code is somewhere in the instruction memory B something something B. And this is somewhere in B something something F. Okay, so if I call BL factorial, it's going to save the next place to return in the LR. So the value of LR will change, right? So it's going to be, when I executed this line, it became 0, B. Well, I lost my way back to here. Did I? Actually, no. The factorial function, as you remember, ends with bx. It returned, it continued. Then I did pop PC, guys. What did pop PC do? Actually, pop PC gets the top value of the stack and writes it to PC. So this is what pop PC do. When I execute this line, what happens is the PC value becomes the value inside the stack pointer, which is, sorry, 3, and stack pointer continues to point here. And if the PC is pointing here, I'm here again. So I was able to return. So I didn't get back using BX this time. I got back using pop PC. That's how you do nested subroutine calls. Okay? So if you're going to be calling a single subroutine, okay, you can use BX LR. That's good. But if you are calling subroutines in a nested manner, calling function inside function, subroutine inside subroutine, then BXLR won't work because each time you do BL, you lose the location of the LR. That's why you save LR inside your function and you call LR. Okay? Good. Any questions? No questions. Biraz düşün bakalım. Okay, now let me just stop the annotations and let me pause the share for a moment because I'm going to be opening an example. I'm going to be showing the solution of this example, if I can find it. Okay. Okay, I'm about to find it. Yes, I found it. So resume share. You can see my screen now, right? This is Kale. As you can see, guys, this was a practice from the previous year's labs. These solutions are available on the website. You can find them. So it basically does is e to the x function, the function that we have seen in the slides. Okay, e to the x function. So as you can see, e to the x by definition is this sum, 0 to infinity. I'm making an infinite number of sums is not possible in a computer program. So what we do is we just make this number small. I mean, we made it 40 as far as I remember in the example, and the results were pretty much good. So what do I do is I call e to the x function. And inside the e to the x function, I do a lot of things. But at some point, I need to calculate the factorial because e to the x needs the factorial of the number that I have. Okay? So I'm not going over the code. You study the code, Please ask me questions about the code in the office hour. But I'm going to be covering the same thing that I've covered theoretically on the slides about what happens to BL and what happens to PC and blah, blah. So I'm going to be putting a breakpoint here. So I'm going to be saving my code, building my code, loading my code, and debugging my code. I'm going to be saying yes, and I'm going to be jumping to that line. So guys, I'm here. So what is my PC value? My PC value is this. Okay. So if I use BL, what's going to happen is my PC value will change to the memory, instruction memory location to here, because this is the first line of e to the x. And the next PC location will be written to LR. Two things happened. So what is the current PC location, which is pointing to here? It is this. So if I press F11 and get inside this code, in LR, I should find a value which is close to this value, right? Because the value inside LR is some random value, initial value. It doesn't have any meaning, okay? It was a leftover from the memory. We don't care what it is. And I do F11. This is F11. So I couldn't do F11. I'm going to press my F11. I'm here now. As you can see, LR has some value, which is most probably, not most probably, it must be the value of the next instruction in the instruction memory. So I have my way back at LR. So this is actually, this is at this instruction memory. This must be, because that's how BL works. But the thing is, I'm going to be calling BL inside this subroutine. I'm going to lose the LR value. That's why I push the LR value inside the stack pointer, okay? Remember this value, guys, please. It was 2A9. Okay, we are going to pop it here to the PC. Now, okay, I've got this value. I can do F10s and just move on. But I'm going to be quickly jumping to BL. Okay, so I'm about to execute BL. I haven't executed BL factorial yet. So the value of LR is not changed yet. So what happens when you do BL? Two things will happen. This will jump to factorial, the position of the factorial. And the next line to be executed, which is here, will be saved to LR. Does it really happen? So I'm not going to be going inside factorial. Let's go inside the factorial. Let's go inside factorial. So I'll be jumping to here, guys, the first line of factorial. So I'm at the first line of factorial. The value inside LR changed. I've lost my way back home. Does anybody remember what was the previous value of LR? It was 29 something. I don't remember. I'm very bad at remembering things. This was, where is it? Actually, we have saved it in the stack. So if you go to the end of this code, I'll put a breakpoint here. I'll press F5 and F5 here and jump directly to PC there. So it's going to be stopping there. So guys, I'm going to get the value inside stack because I haven't used stack. And the value, there is only one value at stack, which should be my return way back home because I've pushed that value. I'll be writing it to the PC. So if you write something to the PC, it's actually jumping, branching. It should jump exactly to where the instruction memory points it. Now I'm jumping ready because I'm going to jump here automatically. It jumped here automatically. This is the idea. This is what I've done theoretically with my pen, with my great talents. And this is what happens really in Kale. And this is how you should debug it. And one question comes to mind. Well, we want to see what's inside stack. Can we see it? Stack is the memory. And starting with next week, I'm going to be teaching the memory organization in Kale. And we will be able to read every single piece in the memory, but not yet. So be patient. You will also be able to read the memory. And before you jump here, we will find where it is written in the memory, that exact number, so that it enables it to jump. But wait for it next week, okay? Next week, we are going to learn memory. But please ask me any questions about this mechanism. Any questions?
Hocam, bu biz yani şu an çok fazla atladığımız için ben bir yerden sonra kaçırdım da LR'daki değer 2E9 değeri vardı. Siz sanırım stack pointer'a gelecek demiştiniz bu değer.
Hı hı.
Tam olarak nereden nereye atlayıp hani
Okay.
F11 yaptığımızda...
Okay, let's go over the example once again, but please remember to go over the examples on YouTube yourself again and do the example on Kale yourself. Okay, but I'm going to do it again and we'll try to explain it in more detail. So it will help, okay, I guess. Okay, I'm stopping the code. I'm restarting the code now. So I hope it's going to explain. This is, I mean, I understand you have never done such a thing in your lives. Nothing in your previous 20-something years of life, nothing similar happened. You haven't jumped to a line of code and you haven't saved something to a link register, I understand. But it is very easy once you get used to it. So I'm saving my code, building my code, loading my code, debugging my code. So the program counter is its initial value. It's waiting for me to say go. I say go, and it stops at the break. It didn't stop at the breakpoint. So let me just stop it again. It should stop here. Okay. Sorry. Okay. So I say it was here. Sorry, it's here because there is another BL, previous BL. That's why. Okay, I'm jumping to this BL. Now, what we said was BL does two things. Okay, please stop me if you don't understand what I'm talking about. The first thing BL does is change PC to the label, which is e to the x. Okay, the first thing it does is this. Any questions about this? Because e to the x is a label, which means it's an address in the instruction memory. And when PC changes a value, it's actually jumping in the code. And it's going to be jumping to the first line of e to the x. Any questions? No. The second thing is write the next PC value. I'll call it PC plus 1 to LR. Okay. What is the current PC value? The current PC value is the address of the current instruction. So this current instruction is written somewhere in the PC. This current instruction is written inside the instruction memory in an address. Which address is that? Actually, since this is the code that we are executing right now, it must be written in the PC and it is value, which means actually PC is at this address in the instruction memory. I'm writing the value from here. Any questions about this? What is the next line of code? The next line of code is let me say this, right? The next line of code is written somewhere in the next instruction memory beneath it. I mean, how much it's something. We are going to know what it is. So it is going to be, if I didn't execute this one, if I didn't jump, I was going to execute this line, right? But I will jump, finish my job, and come back. That value is being written to the LR. So I'm going to be going inside this code, and I'm going to read the value inside LR. That should be this value. So let me do this. Let me do F11. And inside LR, let me just, sorry, I'll get them to the same place. So I'm inside PC now. Sorry. Ne oldu ya? Niye böyle oldu? Okay. Annotate. Now it makes sense. So guys, what do I have in LR? This value, which means actually this was that value. Okay. Any questions about it now? This is my way back home. Any questions? I mean, I don't remember who asked the question, but I'm asking specifically to you. Any questions about this part?
Yok, anladım
okay.
hocam.
Okay. Now I continue. So I'll get down. Sorry. Ekranım kilitlendi benim. Yes. Can you hear me?
Evet hocam.
Okay. Kilitlendi de arkadaşlar. Kontrol edemiyorum Zoom'u. O yüzden acaba hala orada mısınız diye emin olamadım. Bir saniyenizi rica edeceğim. Okay. Zoom cevap vermiyor arkadaşlar. Zoom cevap vermiyor. Stop share. Bir stop edeceğim. Bir daha stop share edeceğim. Okay. So we are at this first line. We lost that values, but they are in the video, so you don't mind. So guys, I'm also doing something else at this point. I'm writing the value to stack, which means there's a value inside LR, which was this value, remember? And there is the memory where I have the stack pointer, right? So let me draw the memory of the stack pointer to here. So this is the memory. Imagine stack pointer is pointing to this location. Stack pointer. And when I push something to the stack pointer, what happens is you write the value of that specific register to that location and you move the stack pointer up. So you just, so I move stack pointer up. Now it's pointing to this location. And I write the value inside the stack pointer, the LR, to here. Sorry. Okay, any questions about this? I guess not. If nothing has happened, imagine I didn't call any BL or something, didn't change any values. In the end, what would happen in e to the x was, imagine I didn't have pop PC here, I had BXLR. In that case, it would return back because BXLR does the same thing with, no, it doesn't do anything same with pop PC. What BXLR does is, imagine I didn't have this because is usually I have BXLR. But this time I have pop PC. Why do I have this? This has a meaning because I call BL inside. Let's see, why do I have BL inside? For example, let me get to the case that, imagine I didn't have pop PC here, I had BXLR. Sorry. In that case, when I come back here, I would be reading my way back from the LR. I have this value. Now I'll be returning back. But I won't have the value that I want in LR in my case, because in between, I call other functions. And each function I call overwrite the value inside LR. How does it happen? I'm going to be jumping there. So, sorry, not pop PC, you're not there yet. Let me start the program again. So I lost where we were. Okay, I'm going to be starting the program once again. Hopefully the values will be the same. Okay, so I'm here. Yes, the values are the same. I'm going inside. Inside LR, I have this. I push the value of LR inside the stack pointer changing, pointing to the next location. Then I'm just moving. The code is doing something. Yes, the value, because the value is 0. That's why I'm sorry. For this specific example, it is not. It's not doing anything because of the values. That's why it's not jumping there. So sorry, I had to make this 6 for some operational reasons. So I do it again. So the values are the same. So now in LR, I have my way back home. So this value is exactly showing to the next line of code. And I go inside and I go do this. And I'm about to call BL. When I call BL, 2 things will happen. The PC value will change to this value so that I jump to factorial. And the LR value will change. But LR kept my way back home to here. If I lose the value inside LR, I won't be able to return, right? But it does. I mean, if you just go inside factorial, the value inside LR changed, guys. However, I kept the previous value of LR at the stack. Okay, that's why I'm keeping those breakpoints. When I want to return back, imagine all these jobs are done. Now I'm pressing F5 so that I jump to the end of this E to the X subroutine. I'm finished. I've finished all my job inside. I've done many operations. Now I want to return back. This guy called me, right? I'm going to be returning back to here. That way back was written in the stack. So I push the value inside the stack and write it to the program counter. Does it really do it? Yes. If you go, it's here in the program counter. It's not exactly the same value, but don't mind it because this is something also about the memory organization. But this is how it does. We are using this push LR pop PC because we don't want to use BXLR, because BXLR looks for the value inside link register. However, when we used other BL operations inside E to the X, we have lost the value in LR. So when you're calling nested subroutine calls, it should be something like this. So let me just put it. Imagine you have a, let me draw it. Imagine you have a main code BL function 1. Okay. So function 1 should be saying push LR pop PC, okay, and inside you have BL function 2, for example, which is the inner depth. Function 2, if it is not calling any other function, can have BXLR, okay? However, if this function 2 guy is also calling somebody like BL function 3, for example, then you cannot use this. Then you should again use push LR and pop PC. But if function 3 is not calling anybody, you can use, sorry. So these are threefold nested calls. Any questions? Okay then, I mean, time is up.